right. Good morning, everyone, or good day to those of you joining and watching this recorded lecture. So today I have the pleasure of welcoming our distinguished lecturer, Professor Dennis Buchanan from Imperial College. And Dennis would take us to the world of creating value and from our mineral projects, and with a specific focus on the strategic and I think critical raw materials. So Dennis, I leave it to you, sir.
Good. Good day to all of you. And let me just get my screen printer. I'm very appreciative of being invited to contribute to what is a very ambitious and successful program online. And I've been asked to talk about the topic, as you can see over here. And I just want to say that I've found this really quite interesting, the discussions over the last recent years around strategic minerals, because in the early 1980s, I acted as a specialist advisor to House of Lords, which is the upper house of Parliament in Britain, when they were looking into strategic minerals in relation to the role of the European community as it was then. I wrote this report. Let me just get it. Here we are. It's a great thing about having a video camera. There it is. Something you can see pretty chunky, lots of evidence. And the conclusion that I came to, well, obviously it was the committee's view, was to be classify a mineral as being strategic. It should then be both critical and vulnerable. That's to say, it had important industrial uses, and that it is vulnerable, and that vulnerability defined from the diversity of sources. And so it is really quite interesting for me to revisit this 40 years later, to find, frankly, nothing has changed. Exactly the same definitions are used for strategic minerals, which is if it's vulnerable plus critical, then it's strategic. And the conclusion of this report was, in terms of this community, the EU as it was, and the United Kingdom, there were only 4 minerals which were strategic, which was chromium, manganese, phosphate, and the platinum group metals. The extraordinary thing is, with the subsequent decisions around this topic, the United States Geological Survey have essentially identified something like 60 minerals, which are all strategic or critical, and this is something like 75% of the periodic table. And so, in a sense, what we are saying is that all minerals seem to be important in that respect. And of course, there have been the European Union approach to this, and the legislation encouragement and the like, which has now probably triggered the interest that we have, and the reason for this type of course. I'd like to go back even further than that to someone whom I greatly admired, and some of you may have heard of, Professor Brian Skinner. And as this discussion around the strategic minerals bubbled up, so President Ford at the time also sought advice on what was meant by strategic minerals. And he brought in the Professor of Economic Geology, Brian Skinner from Yale University. And he wrote quite an interesting paper, which I still use, which is essentially, in a nutshell, how does one define mineral deposits? So here we go now, this whole question of the origin of mineral deposits. And of course, all strategic minerals come from mineral deposits. So it builds in the whole area of economic geology. And so this is the current list of critical minerals for the United States. And you can see the sort of proliferation here of metals and, well, metals in this case, and there's a bit of a semantic issue around their metals or minerals, but these are metals, of course. And there is a sort of a subset from that as well. And I've got a note here that of these, antimony, manganese, tantalum, titanium, tungsten, and vanadium might be considered from the United States the most vulnerable and critical. But there's also gallium, germanium, graphite, heavy rare elements, and that whole bunch there, lithium, scandium, tin, and zirconium. Now, I'm not going to keep repeating all these names. Some of them are unpronounceable, particularly the rare earths. But to step back a little bit and to see how this all fits into the investment environment, value creation, and in particular the role of mineral processing, extractive metallurgy, both pyrometallurgy and hydrometallurgy. So that is, if you like, a high-level historical context. And what I like about Brian Skinner's approach is he talks about the origin of mineral deposits, and he's playing with words here. Of course, as an economic geologist, he understands that there are the chemical, physical processes that result in exotic concentrations of specific metals in the Earth's crusts, and these then provide the basis for subsequent exploitation and mining, and these can support a viable business. I mean, that's what it comes down to. So there is that origin scientific, and then there's also the economic aspect. What makes a mineral deposit in our terminology, and if we take it that it can support a viable business, then that is then economic. So what he said was that actually, when we look at the Earth's crust, we can see that over 99% include elements which in practice we can't really run out of, because we live on the crust. And if in extremis we need to find iron, calcium, magnesium, sodium, potassium, titanium, manganese, and phosphorus, then we can find this stuff anywhere. It's not geologically exotic. And he calls these the geochemically abundant elements. And those are, as you will see, particularly things like iron and aluminium, the industrial metals that we can exploit pretty well anywhere. And the importance of the geochemically abundant is that we have this normal distribution of abundance, or in our terminology, grade. And as we reduce a cutoff arithmetically, we will find that the proportion of the Earth's crust where we would find these metals would increase geometrically. So as we lower a cutoff grade, so we can expect to have a larger and larger resource. Now, the corollary of that is, of course, is that we increase the cutoff grade, then the occurrence of high quality, high grade metals associated with abundant, geochemically abundant, decreases, and therefore becomes increasingly geologically exotic. So Simandou is obviously, a unique in the sense of the quality of that is almost pure hematite, and we don't find too many of those. So in a sense, in terms of diversity of source, then the geochemically abundant, presumably on this basis, and I agree with it, are less likely to be classified as strategic minerals or metals. And then, of course, we've got the rest of the periodic table. Now, I've run an MSc in Metals and Energy Finance. We included oil and gas, the hydrocarbons there, and we are dealing with the energy transition. At Imperial College now, we've taken the view that we aren't able to support research or teaching in the field of hydrocarbons because of global warming and the concerns about encouraging the energy transition. And so we're now looking in terms of that component of energy, looking at other aspects, which are the battery metals being one, and then all the electromagnetic issues go around electric vehicles and turbines and the specialized metals, particularly supermagnets that we need for that purpose, and flow batteries. And so it's been a very exciting time over the last decade looking at this energy transition. And so in terms of the origin mineral deposits, the geochemically scarce metals need also to be considered in relation to their geological association, which is the transition metals will be associated particularly with sulfides, which act as a collector. The sulfides themselves can be liberated and separated using froth flotation. And we've got the thermodynamic constraints over here because they will react exothermically. But we also do have, particularly in the example I given is nickel, which will also be associated with the silicates and go into atomic substitution. And the liberation of nickel from that is an endothermic reaction. So we've got an energy boundary within this, which takes into account the whole area of thermodynamics, which actually is my area of specialization. I did my PhD in phase chemistry and thermodynamics. So we, I think, come back, if you like, to this aspect, and it's been pointed out that the latest USGS list of strategic minerals essentially incorporates 70% of the periodic table. So, you know, we've got to keep this thing in sort of proportion, is that, you know, if anything in this periodic table is used for industrial purposes and or will, that's not strictly true. Not there are some which are not industrial uses, but a lot of them are. Then those theoretically would be strategic. So we've got to sort of get a grip on this so that as professionals, we understand what are the real drivers behind this in terms of investment decision making. So this is this boundary condition where we have an energy boundary here for nickel, where there are vast resources of nickel, vast in nickel laterites all over the world, with nickel in substitution in silicates and in particular the mineral olivine, whereas traditionally the deposits that we would go for, and in Fennoscandia there's some lovely deposits around nickel sulfides, and these in turn are associated with platinum group elements. And so these will, we can recover those by liberation from a gangue. We can put those through flotation systems, and we can then put them into smelters, and we can recover the nickel with the energy balance on our side. To extract nickel from laterites, it's the opposite problem. We need a source of cheap energy. So the geochemically scarce elements is, of course, the area where a lot of us will have worked in, whether it be copper, nickel, zinc, lead, and the like. So in terms of value creation, what we've got to do is to be aware of the developments in the extractive metallurgy side, which is a sort of a central theme that I want to carry through here. So in the case of nickel laterites, these are exploited in various parts of the world. And the ones I'm quite familiar with, Western Australia, where you've also got weathering in terms of the very ancient land surface there. So you have easy mining, you can use backhoes, you can use rippers, you don't need to drill and blast to the same extent. And also you have with the weathering, we have alteration to chemical processes where olivine is broken down into goethite, hydrated silicate, and in terms of that into nickel limonite, and that goes into a thing called high pressure acid leach, and that requires some sort of heroic hydrometallurgy in order to extract the nickel. And that is very energy intensive. So for the geochemically abundant metals, as we reduce grade, we can expect to have that geometric increase in the size of the resources, but we also have more energy going into that in order to liberate from the geochemically abundant. In the geochemically scarce, particularly we're dealing with the transition metals, then we will hit this mineralogical barrier, and we really don't want to be the wrong side of that unless we've got cheap sources of power. And the example I've given is, of course, nickel. So this is sort of a thread that I will want to pick up as we go through. Now, I've do a lot of teaching around mining finance and the role of the technical and financial aspects, the interrelationship between the two. And I have had delegates say, look, a very interesting course, Dennis, but can you give us in a nutshell, what we should be looking for in terms of investment opportunities and to get the real value from opportunities that come our way? And so I've put together this little diagram with the main driver over here of metal price, one in the case of nickel, and we want to look at why we have this slump in nickel price and why copper is going in the opposite direction. But if we look at the geochemically abundant and we calibrate that with against the value of the pure product, then a barrel of oil in terms of its weight, in other words, tonnage, would require something like 6.33 if you have 1 ton of oil. And that would be worth about $600 for a ton. Coking coal is about 300, iron ore about 120, fracking sands about 50. And within that concept over here, if you're looking at the most expensive commodity, it's what comes in a bottle, a plastic bottle, and a liter of this stuff. In most places, if you go along to a motorway service station, will cost you about $1. So for a ton of water, you're going to be paying at least $1,000. So you can see that these are essentially, the only way you make money from these is by pushing large volumes of it. For the geochemically scarce, I've looked at nickel, copper, and zinc. So if we take pentlandite as being the main product, then the content of nickel at $1,700 a ton for nickel would be worth about, based on the stoichiometry of pentlandite, about $4,000 for a ton of nickel pentlandite concentrate. On the same basis, a ton of chalcopyrite concentrate with the stoichiometry would be about 250, 280. And up here, we're dealing with zinc and sphalerite at $1,300. I'm using 7,500 for copper, which is a bit lower. That would be worth 1,000. So what we're saying is, in terms of value creation, if you want a mineral deposit, then you want to have a nickel sulfide running at about 0.3, 0.4%, a copper deposit running at about 3%, Kamoa, Ivanhoe's DRC copper deposits are running about that. So this is just a rule of thumb. If someone says we've got a deposit running at 3% copper, just grab it. This is good quality stuff. And the same with the zinc, as you're posting 10% on a zinc lead deposit, then go for it. So, as a rule of thumb, the relationship between grade and value is important. The drivers on metal price are just so diverse as really to defy rational analysis, in my view. Why did this happen here? Well, what has happened is Indonesia has suddenly started using cheap power to use pyrometallurgical processes to exploit their huge laterite deposits. Never any shortage of laterite. They've just decided they're going to exploit it. And that has hammered the nickel price. The copper story is different in as much as with the energy transition, we're looking at a electric vehicle using 3 to 4 times the amount of copper in its winding and its wiring. In these big wind turbines, they're using a lot of copper. Distribution would be probably using aluminium, not copper, but that is driving the copper price. So each will have its own particular economic framework. And to my mind, the only way really to handle that with any level of objectivity is to consider the downstream extractive metallurgy, mineral processing aspects. When things go wrong in mineral projects, it's invariably in that area, in my experience. So the drivers then do take into account prices. Volatility can be handled using the techniques of quantitative finance, and that includes the use of derivatives and hedging when it comes to doing debt finance. And the whole tradition of quantitative finance is what I'm interested in particular the interface between the tools, the stochastic mathematical tools of quantitative finance, and the uncertainties of estimation of grade using the techniques of geostatistics. Both have the same mathematical foundations, and there's that interaction. So that, in terms of new business development, involves companies taking a view on what prices are they going to use. And I suppose you'll have to take into account historical prices, provided you haven't seen some sort of major move in terms of usage. I suppose a starting point for any financial assessment is the spot prices today. So there is a transition in our business through to the social license, ESG, environmental, social, and governance issues, and in particular the social license, where notwithstanding the importance of lithium in Europe, JADA in Serbia has run into problems because local people don't want that mine on their doorstep. In the case of Indonesia, the government has taken the view that this is their resource, that the local communities, they seem to accept that, and they are using a pyrometallurgical process to produce nickel, and just swamped the nickel market. And I don't see any change in that. I mean, the ICMM, which is the sort of trade union, the lobbying and the standard setters for the international mining industry, have got this very able CEO who is actually on a mission to explain to the industry that the resources don't belong to them, they belong to local people. And I've been hugely impressed with the efforts made in Lapland by miners and explorationists to communicate effectively with the Simi people that any development there is going to take into account traditional ways of life. And so the whole piece around the moral case of mining, which is effectively needed to add value, because without the social license, without the mining license, no matter how sophisticated both our financial modeling and our conventional engineering, we're not going to be able to develop our resource. and the Indonesians, seem to have got it right there, although there's been very significant impact on the environment there because of the nature of the mining, which are essentially, here we go again, laterite, nickel laterites. So here we go, battery metals, people, and in particular the dominance of the business by use of lithium batteries. And this is a sort of breakout of what goes into a standard lithium battery. There's the critical thing is not just the cathode and the anode, but also the casing that is associated with it and the components that go into that. But the classic approach is looking at the cathode, which is the lithium sitting there, which, as you can see, is quite a small proportion of the overall. There's nickel, which we've talked about quite a bit, and cobalt, manganese. And these are the sort of recipes, these are the different alloys that can be associated with putting together the appropriate electrochemistry to give you the maximum energy balance within these products. And these are constantly changing. And so one just has to be very aware that from the electrochemical point of view, lithium and sodium are very close to each other in the periodic table, have very similar electrochemical properties, but sodium, of course, is very much more difficult to handle. That's why they've chosen lithium. So there is an area that one needs to watch out, which is colleagues working in the field of electrochemistry, because they're coming up with new ideas about what may make a better sort of battery. So that is, if you like, setting the scene in that respect. And then there is another point too. So I'm not sure about the full profile of all the participants in this program, but I'm assuming that we are mostly from a minerals and mining background. That's geologists, mining engineers, mineral process engineers. But we've got to also recognize that when it comes to metal prices, we are used to dealing with the London Metal Exchange, for example. We've got good delivery onto the LME, which is typically 2 nines for our metal projects. But we've got to remember that that is just a starting point. That's just a raw material for the electrochemists in terms of battery technology and battery electrochemistry. And they require a much higher degree of purity. And for those of you, who have a chemical background, go to the laboratory, and of course there are little bottles, Johnson Matthey bottles, which are spec pure chemicals, and they give the composition there. So going from 2 nines to 4 nines is non-trivial and very expensive and very difficult to tease out from any real source what the costs are. So but in terms of our financial models, we can't necessarily put in price assumptions. And if we have to start building models around the costs of the facilities for refining, then that is a whole different part of a financial model. So we've again, going back now to the periodic table, and you can see the level of complexity that is downstream of our business, which is producing metals for a metal exchange. So there is an opaqueness about the end user, the offtake agreements with the refiners, and many of these are sort of confidential. Many of them require chemical processes which are quite toxic. And so here is our world that we're working with amongst all the hype about the EU needing to go in to support the development of critical minerals. And we can almost certainly say that cobalt is a critical mineral because of its role in battery technology. But here we find that we've got the sort of rather unhelpful comments from the inspectors, who just reminding the industry about dust levels, and that the dust levels in these facilities purport to exceed the limits that are applicable, and that's in Europe. Now, that doesn't apply to someone else who was also producing cobalt, who are not constrained. Now, I'm not suggesting that in Europe one should lower one's standards if those are shown to have harm to human health, and clearly that needs to be observed. But what it will do then, of course, is it'll put a lot of pressure on the existing facilities, and it will push the vulnerability away from Europe, or increase the vulnerability, because the capability is then being taken up elsewhere and outside a particular geographical boundary, not just Europe, but it'd be the UK and also the United States. So, here is now just a sort of a background on the use of battery technology, the whole world of electric vehicles, and there is, enormous interest in society around this. And one sort of aware. I personally, I've got a very nice lodge up in Scotland. I live in Buckinghamshire, and sadly, a vehicle will not get me up there on one charge. So I bought myself a nice internal combustion, or at least nice motor car with an internal combustion engine with a range of 600 miles. So, that's a particular decision that I've made, but not everybody sees it that way. So in terms of sources of lithium, I've visited Buchanan in Zimbabwe many years ago in the early 80s, where spodumene petalite was produced there, and it was used in Corningware. It was a ceramic which could withstand thermal shock. So you could buy this crockery, you put it into your Aga oven at high temperature, and the thermal, going from room temperature up to 200-300 degrees Celsius, you didn't find that your beef stroganoff is now sitting inside of your oven because the receptacle is cracked because of the thermal shock. But it did seem to me an obvious source of lithium, and that is exactly the case. In the case of the kaolin industry in southwest England, there are great big mountains of waste rock, all of which contain the mineral lepidolite. And so Cornish lithium have gone back into those old granite quarries, and they had recently announced that they've got a pilot plant that is producing lithium hydroxide for lithium batteries, and good luck to them. So we've just got to be careful when you put the financial models together. I'm lucky I had students who've been working on this with dissertations over the years. You've really got to watch your stoichiometry here, because you can see the stoichiometry here. So that has got to be related to the mass. So you can get an assay back of running a 0.3% lithium, but you've then got to watch your mass balance all the way through, because you're mining tonnage, and you're then getting your revenue as lithium hydroxide. And so that is then tons of lithium hydroxide, and it's a lot of fun making sure that your mass balance is correct. It's not trivial. So just to warn anyone who's getting into that business, do watch your mass balances here and your stoichiometry. There is a growing discussion now about the ethics of using the brines from the Atacama. It's desert, and so this is, it may well be a brine, but it's still water. And so the aggressive handling of that resource and the building of evaporitic ponds and using pumping to extract from the aquifers is starting to affect quite delicate ecosystems. And there has now been a growing debate around that. But with the realization that lithium is associated with all sorts of geological associations, and the investment in those deposits and the production of lithium hydroxide, you've seen that, if one of the key drivers, and obviously it is, a key driver is the metal price over here. It is now traded on the London Metal Exchange, and it is really nothing like the sort of peak that was behind a lot of the drivers. And of course, what's inevitably happened is you've got now overproduction of lithium and the effect that that's going to have on anyone wanting to come in at this stage and add to that supply. So looking at the broader aspect of the periodic table, and I've covered some additional ones here, and there is this notorious heavy mineral coltan. It's a heavy mineral, so very easy to produce a concentrate. It is part of a solid solution. I've done some work on these deposits, and you have the solid solution of niobium and tantalum, and you can see the rather nice zoning that you can pick up over here. And so you've got to separate. So the separation one from the other is a factor, but the coltan is very often associated with uranium. It's a common association. And so sometimes the concentrate can also be a very high radioactivity. So it's not easy stuff to handle, this coltan, because of the uranium signature. You've got to be aware of that. So there is an effort to try and have ethically derived sources in the same way as you have with diamonds. But the importance of these elements is that they do offer an alternative to lithium batteries. And the takeaway here is just watch one's flank on the electrochemists, because they say that a titanium niobium battery is much better than a lithium battery. It has a much higher energy density. And it has struck me that with lithium batteries is that when my internal combustion engine takes me and my luggage and the office dog and my wife across the border into Scotland, I'm now down to a third of a tank, and so I'm not dragging a ton of battery. If I was in an EV vehicle, I'm still dragging a couple of tons of absolutely dead inertia across the border into Scotland with me, and there's nothing much I can do about it. So if you can change the energy density, then that is, the mechanical engineers are now going to start scratching their heads and thinking, well, why aren't we using these as much better batteries because of a high energy density? So I think we're dealing with quite a fluid situation. I mean, the whole area of rare earth elements, as you probably know, is there is nothing rare about a rare earth element. They are very common throughout the geological record and geographical locations. They're all associated with almost unpronounceable names, so I'm not going to go embarrass myself by trying to repeat them. But in essence, they form a critical pond. I mean, just thinking, I changed this image because not many of us use hard drives anymore. I don't think it's all solid state, isn't it? I know my new laptop isn't humming away to itself anymore. But it is a critical part of the electric motors in electric vehicles, and of course in the turbines as well. So they are important, And these are the Presidium, neodymium are the critical ones. Dysprosium, I'm told, is all part and parcel of the hydrometallurgical process of purification. So this is my area of interest, is financial modeling. And boy, do I scratch my head with a rare earth element project, because essentially they are traded. The only value you can get is in rare earth oxides. The value of a rare earth oxide, which incorporates these critical individual elements, it can be determined by the proportion of each, and each have different prices associated with them. And so the determination of the revenue assumptions will, in all the models I've seen, exclude what is the value and the essential assumption of revenue from the individual elements. So all you will get is the basket price for the oxide, and there has to be subsequent separation one from the other. And I mean, this is a very, very dynamic, fluid narrative. I thought, right, when I sent through to Elisa my presentation, I suddenly realized, whoops, it's already out of date. So, yesterday we saw this announcement that Saudis are now getting involved. So they're going to pick up. Mountain Pass was closed in 25 years ago on environmental grounds. The assets were picked up by MP Materials. Have a look at their share price. I mean, whoever invested in MP have done extremely well, because the US Department of Defense have now given them a guarantee price and invested in this. Now they will produce rare earth oxides, and now that the US has done a deal with the Saudis, they're going to build themselves a nice refinery, which will then split out these. So I mean, it's never underestimate the power and innovation that the US brings to these types of arguments. And it's just transformational overnight, yesterday's announcement on the future of rare earth elements. So there we go. I've got a few more supplementaries to put in. The interesting thing about vanadium is it's used predominantly for ferroalloys, but it's also used for flow batteries. And the flow batteries are important in as much as they can't catch a light. So, we all know the electric vehicles do have this risk because they're fluids. But of course, water's heavy, and they are being used as sinks for balancing electric grid. I know, referring back to Scotland, with all the wind turbines, they're growing all over the show in Scotland, but they're rotating without actually producing any power because the grid isn't in place. Scotland doesn't consume enough electricity to justify the investment in the turbines. And they have to put in grid to get it down south. And so they're building a lot of these things, which are storage, so that they can at least store the batteries. And they're also resuscitating the hydro storage facilities. So I've talked about the drivers over here. I'm going to finishing off very shortly, Lisa. We look at them in terms of our business, which is the cycle from exploration through evaluation, pre-development, development, production. And so you would need to look at where you are in your projects, depending if you've got early day exploration in rare earth elements. Well, think very carefully about the markets where it looks as if people are going to leapfrog right across into production without even going through these preliminary steps. and looking at also where you are in terms of valuation and the value added against time and the time that it will take. If you're still in the exploration stage in critical minerals, it could be 15 years before you're actually into production. But if you are in more advanced projects, then these inflection points have a lot of value in it. So I leave you with those thoughts. If you want to see a little bit more around this and how it relates to actual mineral companies and valuation in terms of share metrics, I've just written up this paper, which was accepted by Mineral Economics earlier this year. And bearing in mind that we will only know the real value of our assets when we actually get the thing into production and we are listed and we see what the market then subscribes to it. That's it, Arisa. Thank you very much. And I'll put my last slide over here. I did
Thank you
start 2 minutes
very
later, so I'm on time then.
Yeah, thank you very much, Dennis, for such a wonderful lecture. I learned quite a bit myself by going through your material and listening to you.